Okay, now it is good to start, you think?
Okay, for me it's perfect.
Okay, hello everyone. Welcome to the second PhD talk of OBERON. We are here to listen to the second PhD talk of Iñaki. I think some of you were not, couldn't join to the first PhD talk that Iñaki talked about the optical systems and optical phenomena. I want to introduce you again. Iñaki is a PhD researcher of the University of Minho, Portugal. He is working on off-axis wavefront modeling of human eyes for different range of age, if I understood correctly. And a bit about his background. His background is in optic and also physics and technologies of lasers. And if you have any questions about optic and physics and technologies of lasers, you can ask him. Okay, in the first meeting, he talked about optical system and optical phenomena like dispersion, diffraction, and scattering, that these phenomena can influence on optical systems and can influence on imaging of the optical systems. And also a very common and very important phenomena that mostly is happening in optical system is aberration. And this is very important, and Iñaki want to talk about aberration in this meeting. Iñaki, if you are ready, you can start. Thank you so much.
I'm ready. Thank you very much for the presentation. I'm going to share the screen. So, can you see it well?
Yes, it is good. Thank you.
Okay, so perfect. So as you know, this presentation is going to be about aberrations. So we should take into account that there are going to be different kinds of aberrations, depending on if we are focusing to the wavefront or if we are focusing to the rays. Only as a little reminder, the rays are going to show us the direction of the propagation of a portion of radiation, and they are going to be always perpendicular to this wavefront. Okay, so these wavefront aberrations are going to be the difference between the ideal wavefront, in this case the spherical reference sphere, and the real one. And these ray aberrations are going to be related with the distance at which the real ray meets the ideal position. In this presentation, I want to talk about the Seidel theory of aberrations, first of all, because I think that it is a quite intuitive theory in order to know what kinds of phenomena can be happening out of this ideal or this paraxial region of propagation. Okay, but first of all, I would like to talk a little bit about this interesting and useful mathematical tool, the power series, with which you can explain some kind of more complicated function with some approximations. Yes?
Sorry, just one thing. In the screen you are sharing, we can see the small screen showing the person who is now speaking, like me.
Okay.
Okay,
so,
good. Thank you.
Thank you very much, Norberto. So, okay, I want to talk about this mathematical tool, this power series, because it is quite useful to explain, to find approximation to functions. For example, this is going to be the order associated to the zero order, first order, second order, and so on. And in this case, for example, if you are trying to find some kind of approximation to this sinusoidal function, you can see that with the first order, this is going to be a good approximation in this small region. but it fails when trying to explain this other region. Then you can introduce another order as the third order, for example, and then you can continue introducing orders to try to find a better approximation. So we are going to try to be doing the same thing, but in this case, the problem is that here we are working with only 2 variables, but in the case of the Seidel theory of aberrations, we are going to be working with 5 variables: the height of the object, the coordinates of the aperture of the system, and the coordinates of the image plane. Then what Seidel found was a way in which he can find the coordinates of the ray in the image plane using a function that depends on the terms of the coordinates of the aperture of the system and the height of the object. This is going to be the shape of this expression that he found for the x and the y coordinates, in which we can see that this is going to be related with this power series, and this is going to be the first order and the third order. So then what is interesting is that that coefficient associated with the first order are going to be related with the paraxial optics. So then the first coefficient is going to be related with the transverse distance between the focus and the image plane, and the second coefficient with the magnification, the height of the image divided by the height of the object. So then the different coefficients that are out of this paraxial region are going to be related with these aberrations. Then these B coefficients are going to be related with the Seidel aberrations, and because of this third order of this series is going to be called sometimes the theory of the third order of aberrations. Then the first coefficient is going to be associated with the first aberration of the Seidel theory, the spherical aberration, astigmatism, field of curvature, and distortion. Some of them are going to be related with a direct image degradation, and others are going to be related with image deformation. I would like to start talking about the first aberration of the theory of Seidel, the spherical aberration. So imagine that we are working in this ideal or paraxial region, then your radiation is going to go to that paraxial focus. But if you are hitting with your rays at different height, you will see that this focus is not going to remain the same. There are going to be different focus associated to different rays at different heights that are hitting in the lenses. If you're hitting with the higher position that it is possible with the limit of the aperture, this is going to be called the marginal ray. Then you are going to see what it is called the marginal focus. If you're able to measure the distance between the marginal focus and the paraxial focus, this is going to be called the longitudinal spherical aberration. And in the image plane, it is going to be called the transverse spherical aberration. If you see how it's going to affect to a system, this one is going to be only limited by diffraction. And in this case, we are going to have higher amounts of spherical aberration. The second is going to be called coma. If we are working off axis, then imagine this rays at this aperture is going to be focused at this point. So if you are able to measure the distance from this to the ideal position, this is going to be called the transverse chromatic aberration. So if you work with a different and smaller aperture, this is going to be nearer to this ideal position. So you are going to have lower values of this chromatic aberration. Okay, so if you imagine that you do this experimentally, you will see that this A ray, this B ray are going to be focused in this point, and this distance is going to be related with this transverse chromatic aberration. And the distribution is going to be something like this, with a higher contribution here, concentration of intensity, and then here with a little bit of dispersed radiation in this chromatic shape. Okay, the other aberration is going to be called astigmatism. Imagine that we are working with this plane, for example, this is going to be called the tangential plane. Then there is going to be a focus associated to this tangential plane. Okay, what it is going to be happening is that in the ideal situation, you're only going to be working with one focus. But because of this aberration, because of this astigmatism, if you work with the rays in this sagittal plane, you will see that you're going to have another focus. You're going to be working with the sagittal focus and the tangential focus. And if you see how it's going to be the image in that positions, you will see that the image is going to be like some elongated lines. Okay, what we are going to be seeing is as you increase the angle with which you are propagating your beam through these lenses, you will see that the distance between the sagittal focus and the tangential focus is going to start to increase with this parabolic shape. And in the case that you have no astigmatism, your image is going to be over this surface, over what it is called the Pethval surface. So the image of a plane is not going to be anymore another plane. It is going to be some kind of curved surface. It is going to be called the Pethval surface, and it's going to be related with the other aberration, the field curvature. Imagine that you have this on-axis radiation. It is going to be focused in this position. But if you work with off-axis radiation, the focus of the light is going to be at some distance from this image plane. Then what it is going to be happening is that your image is going to be well focused in this region here. But then you are going to have some kind of the focus on these regions. So you will see the image of something like this. You will see that the image is going to be focused here, and you are going to have some kind of the focus on the periphery. Okay, the next aberration and the last one related to the Seidel theory to these aberrations is going to be called distortion. The distortion is going to be that imagine that you're generating the image of this object, then the relationship between the different points of the object, the relationship of the size of the magnification, it is not going to remain the same. So then what it is going to be happening is that here, for example, you're going to have the case in which the magnification in this region is going to be smaller than in the center. So you're going to have this barrel distortion. Or in the case of this, that you have a higher magnification here in this region, you're going to have this Pincushion distortion with this shape. There are going to be other aberrations that are going to be related, for example, to the dispersion. Remember that we are going to have different angles of refraction associated to different wavelengths. Then we are going to have different focus associated to that different wavelengths. If you measure the difference from those focus, you are going to be able to measure the longitudinal chromatic aberration. And in the image plane, it's going to be called the transverse chromatic aberration. If you are generating, for example, the image of an off-axis object, you will see that you will have different heights associated to different wavelengths or different magnifications associated to different wavelengths. Then this is going to be called lateral color. Now I would like to talk about other phenomena that can affect aberrations of your system. This is the design of your lenses. Okay, commonly you're going to be working with a spherical surface, the one that follows this circle distribution. But in the case that you you can introduce, for example, other designs. It can be, for example, a conic surface as a parabola, hyperbola, ellipses, or others. And if you want to be more precise and you want to make other kind of modifications, you can introduce other degrees of asphericities, for example. This is going to introduce changes on the spherical aberration, astigmatism, and distortion. And then you're going to be able to correct, for example, some contribution of a spherical aberration, changing the shape of the design of your lenses. Now I would like to show you a little example of how can you calculate this Seidel aberration. So imagine in this case with this small model of the human eye, imagine that you will need to propagate two specific waveforms. One is going to be on axis, the other is going to be off axis. Depending on the book, they are going to be working with one ray or with two rays. In this case, with these two rays, we are going to be working with the marginal ray of this on axis wavefront. Then this marginal ray is going to pass through the edge of the aperture, in this case, the pupil, and the chief ray associated with the off axis wavefront is going to be propagated through the center of the aperture. Then imagine that you are working with the anterior surface of the cornea. If you want to calculate the different Seidel coefficients, this is going to be interesting in order to calculate, for example, the different wavefront aberrations. So with these Seidel coefficients, we can see that being focused in some parameters, for example, the height at which the ray hits the surface, with the angle of refraction with the incident angle with respect to the optical axis, the index of refraction of both media, and then you can have an intuition of the values of the different Seidel coefficients associated to the spherical aberration, astigmatism, the Petrel curvature, the field curvature, and distortion. And now we are going to see how can we calculate this wavefront aberration. So imagine we are going to be working with this system, with the entrance pupil and the image plane. Then we should introduce some kind of conditions in order to make the calculations. One of these conditions of your optical system is going to be that it needs to be rotationally symmetrical. So then you are going to be working with 4 variables, 2 related with the entrance pupil, or another 2 related to the image plane. And then you can make this combination of the different variables in order to assure that your system is going to be rotationally symmetrical. I'm going to make you a little demonstration of how it can be possible to be rotationally symmetrical, for example, this coordinate, and you will be able to make the same for the other coordinates. Okay, so if we apply a rotation, mathematically it can be explained in this way, this for the entrance pupil or this other for the image plane. If you calculate this x squared and this y squared, you will get this expression. And if you make the sum of both of them, you will get this expression here. So there is not going to be any relationship with the angle. So then you can change the angle that the result remains the same. So, and you can do the same with the other coordinates. So now that we are working with this system, because of this symmetry, you can be working, instead of working only with working with these two coordinates of these two variables, you can eliminate one of them, because with this one, because of symmetry, you are going to be able to calculate the other. So then you are going to get this expression for the wavefront aberration, and then this is going to be again a power series. In this case, these terms are going to be of second order. This order is going to be of fourth order, and you can change, for example, this in Cartesian coordinates, you can change it in polar coordinates. And then what it is going to be interesting is that in this way, you have been able to discretize different phenomena how are going to be affecting to the shape of the wavefront. For example, this first term is going to be related to how is going to change the shape of the wavefront with the focus. This other is going to be the tilt of the wavefront, or for example, a retardation or a constant value that you can introduce to that wavefront. These others are going to be directly related with the aberration that we have been talking about. This is going to be related with the spherical aberration. This is going to be related with coma, astigmatism, curvature of field, and distortion. So this is the point that it is interesting of the Seidel theory of the aberrations, and is that Seidel make the calculations in order to get directly a different theorem for the different phenomena that can be happening. You obtain directly in a natural way the different aberration with the different polynomial that was employing Seidel. Then you have here this spherical aberration with the same function, the same way with coma, astigmatism, the field curvature, and distortion. Okay, so now we get that if we calculate the different Seidel coefficients, you can calculate the coefficient of the wavefront directly. And this is very interesting because in this case, if you have the coefficients, you are going to be able to compose this wavefront, because these other parameters, these other variables, you are going to define them, because the parameters related with the entrance pupil or with the image plane, probably you are going to give to the calculation. So you need to get the different coefficients to compose the wavefront. And the different wavefronts are going to be with this shape associated, for example, spherical aberration with this R up to 4 is going to have a shape like this one, comma, stigmatism, field curvature, and distortion. But the problem here is going to be that in the Seidel theory, for example, the focus is not going to be considered an aberration. And then if you want to calculate it, you can do it manually. I want to show you a little example with which I'm going to demonstrate you that you can calculate it, and that this functional form is not going to be something random, that you can demonstrate that this is going to be the shape of the wavefront. So I'm going to try to demonstrate this, the wavefront aberration with the focus. So now imagine that you have this wavefront, this spherical wavefront that is going to be focused into this position. So then you are going to be working with this. This is the equation of this spherical equation, focus into Z equal to R. This is going to be. And then we want to get, in terms of this entrance pupil, the wavefront aberration. So we are going to try to get this set in terms of X and Y. So we can make the calculations and we get this expression to this wavefront perfectly focused. So this is going to be some kind of parabolic function. And what I want to show you is that if you now change the observation plane, you introduce some kind of the focus, this R is going to pass to be R plus epsilon. And then you're going to be working with this function. So if you take as a common term this value here, you will get this expression. And you can make this little approximation in order to be easier to work with. This is the geometrical series. And you get this expression to the wavefront. This is the point that is very important, because this shape is going to be the same as the spherical wavefront, but with a new term. So this term is going to be related with the focus, and you will see that the focus term is going to be a constant multiplying X squared plus Y squared. So then the shape is going to be the same one as the one that we obtain using these different series power and the decomposition of these elements. So this is why the shape is going to be done by this R square, okay, the radius of the entrance pupil. I haven't said it, but in this wavefront aberrations commonly, they are going to have the radius between 0 and 1, so it is going to be normalized. And now that we have seen the different Seidel coefficient and some calculations, I would like to talk a little bit about the thermic polynomials, okay? They are going to be quite useful to work with, but the problem is that commonly they are going to be less intuitive, okay? So they are going to be defined again as a sum of different coefficients multiplying different polynomials. These polynomials are going to be compounded by two terms. The first one is going to be related with the radius and the other with the angle. This m is going to be called the angular frequency, and this n is going to be called the radial order. So then they are going to be represented commonly in this pyramidal shape, and we will see that this is going to be called piston, tilt, astigmatism, the focus, trifold, comma, tetrafold spherical aberration, and the second order astigmatism, for example. So these are going to be related with what it is called the low order aberration, and this order to the high order aberrations. We can see that there is going to be piston, tilt, astigmatism, defocus, comma, and spherical aberration as in the others that we have calculated before, but they are not going to be exactly the same, because as we can see here, this astigmatism, for example, is going to be divided in two components, orthogonal between them. This is the oblique astigmatism and the vertical or horizontal one. The same with comma is going to be divided in the vertical and horizontal one, and this is going to make it sometimes to be less intuitive, as we are going to see. But they have quite interesting properties, as for example, that they are the system is going to remain rotationally symmetrical. So if you rotate the system, the polynomials remains the same. They have this orthogonality that is going to give to this polynomial quite interesting mathematical properties, and there is going to be inside of them some kind of aberration balancing. Okay, so I would like to start talking about a very interesting magnitude that we are commonly calculating with the aberration. It is going to be called the root mean square error, the RMS, and it is going to give you an intuition of how aberrated your wavefront is. Okay, commonly, if you are working with the Seidel aberrations, you are going to be working with a shape like this one, but because of this orthogonality, you can work with them in this way. You can make the square root of the sum of the different, the square of the coefficients. It is quite easier than this one, and you are commonly going to ignore the contribution of piston and tilt. Okay, and this is going to be something like in this case, if you have this, for example, these coordinates, they are going to be orthogonal. They are going to be making here 90 degrees. So if you want to know the distance to this point to the origin, it is going to be calculated in this way. But this is because of this orthogonality. So you can do quite the same procedure. In this case, you have here the astigmatism and the focus. They are orthogonal. So if you want to calculate the root mean square error, you can do it in this way. But if you want to know the contribution of each coefficient, you need to study them individually. Okay, now I would like to talk a little bit about aberration balancing. Okay, this aberration balancing is because commonly the best situation that you can be in your optical system is to be working without any aberration related to the optical quality. But in the case that you have some aberrations, the best situation is not to isolate them. For example, if you are working with a spherical aberration, it is better to have a little bit of the focus, some component of the focus, in order to increase this optical quality. So this is something that is going to be inside of the definition of the spherical aberration, for example, in the Cernic polynomials. Here you have the shape in the wavefront with the Seidel theory that it is going to be this radius up to 4. But here you have this contribution of the spherical aberration, another from the focus, and a constant term that could be related with piston, for example. This is something that makes sense because imagine that you have this system with this perfectly focused here, but you have this amount of spherical aberration. So the best situation is to put the observational plane instead of here to put it here, because this is going to be the region associated with the circle of least confusion. This circle is going to be the region at which the distribution of light is going to be nearest to the ideal distribution of light. Okay, so this is something that is going to be happening here with other polynomials, as in the case of comma, for example. There is not going to be the pure comma of the Seidel theory. This is going to be comma with a little contribution of tilt. In the second order astigmatism is going to be the same. There is this contribution of the first order astigmatism. And in the case of the spherical aberration, there is going to be a contribution of the focus and piston. Okay, so as a little overview, we have seen that we are able to express the different wavefront aberration, having into account the different coefficient associated to the different Seidel aberrations. You can do the same with the Cernic coefficients, and we have seen that now with the Seidel theory, you can decompose the different phenomena in, for example, a spherical aberration that is going to be the change of the focus with the aperture. So if you measure this from the marginal focus to the paraxial one, you will be able to calculate this longitudinal spherical aberration, for example. If you work off axis, you will see that there is going to be appearing this comma. That is going to be the distance from this point to the ideal one. And I haven't said it, but commonly you are going to have comma if you're working off axis, but on axis, if you have some kind of tilt of the centration, there can appear also on axis comma. There is astigmatism. Astigmatism is going to be appearing mainly if you work off axis, or in the case that the lenses, in the case of the human eye, they are not well manufactured, you will have astigmatism on axis. But in this case, we are going to be working with two focus associated to two different planes, in this case, the tangential plane and the sagittal plane. And in the case that you are not working with any astigmatism, the image is going to be generated over this pephal surface, and it's going to be because the different rays are going to be focused in these points at some distance from the image plane in the off-axis propagation. So the image will be well focused in this region, and in this other you will have some kind of blur or the focus. And finally, distortion. Remember that the different points are not going to remain the same magnification to the different points. You will have, for example, in this case of Pincushion distortion, that you will have a higher distortion in the edge that compared with the center, and that this kind of phenomena are going to have associated this wavefront aberration with each different shapes. Okay. And that now we have seen that there is going to be some kind of relationship between the Seidel aberration and the thermic aberration. You will have the same names, but they are not going to be exactly the same, because remember that in the spherical aberration, you will have the focus and you will have other contributions, and you will see that, for example, in this case of common astigmatism is going to be divided in orthogonal components. Okay, but in the thermic polynomials, you will have the contribution of the focus, tilt tip, and other contributions. So the thing is that the thermic aberrations, thermic polynomials, are going to be less intuitive. In most cases, they are going to be more useful than the Seidel aberrations. But in order to know what kind of phenomena can be happening out of this paraxial region, I think that these Seidel aberrations are quite useful. Remember that if you want to calculate how aberrated your wavefront is, because of this orthogonality, is going to be more useful with the thermic aberrations. And remember that if you are working with the system, the best situation is to be working without any aberrations. But if you have some kind of aberrations, there is going to be other situations like comma interacting with tilt, for example, in order to increase the optical quality. This is the bibliography that I employed. So as I took different demonstrations for different books, they were different notations. So I hope that everything was more or less uniform. And I only have to say that thank you very much for your attention. And I hope that you enjoyed the presentation. And I'm so sorry if I went so fast, but that's it. Thank you very much for your attention.
Yeah. Thank you so much, Iñaki, for your talk, for your interesting talk. Yeah, it was very fast.
I know it. I'm so sorry. It's my fault always. Yeah, but
No,
I'm trying to work on it.
Thank you so much. Thanks a lot. And if anyone has any question,
I have one question. Okay.
Yes, please.
No. What do you think? Because in OBERON, you are trying to model in the eye. Okay. What do you think is better to use, the Seidel or the thermic aberration for? Hello, Anna. For the eye, what do you think is best? What will be and why?
What I think is, I have seen some quite for the human eye, for example, as we are always working with imagine in order to calculate or to have a more intuitive idea of the refractive error, or to calculate directly the defocus, because it's going to be all the contribution of the defocus inside of this Seidel aberration is not going to be divided in difference. I think that because of it is more intuitive, I would say the Seidel aberrations. But then I have seen another point that is interesting, and it is that the Seidel aberration depends also on the field, on the image plane, and the thermic aberration only depends on the entrance pupil. So I think that it could be there could be some interesting properties on this dependency. I don't know if you think so. And I don't know, what could be better. What do you think, Norberto? What do you think?
Okay, this is what I think. Okay, normally Seidel aberrations are defined for symmetrical spherical surfaces. Okay, and the eye and the cornea is not totally spherical. Okay, could have, for instance, clinical, what we call clinical astigmatism, could be a toroid, okay? Two different radius of curvature. So we'll create the astigmatism, but this is what we call the clinical astigmatism, okay? It will be just a spherical one, perfectly spherical. Another astigmatism will be created when we use off-axis object, okay? But even with a real cornea on axis that has astigmatism, you have astigmatism. So that will not be, cannot be expressed in shaded aberration, because in shaded aberration, the only astigmatism is when it's off axis. Okay, understand? So this is a little bit tricky. So I think in general, Wernicke's are could be probably a better way, okay? Because it's not rather than it's symmetrical survey. Also the lens, okay? One problem that has the Wernicke's is normally they are defined for a pupil radius, okay? Well, it's normalized. So, but the problem is that the eye is changing the pupil, okay? Like Maria knows very well that when the eye, for instance, accommodates, there are meiosis, okay, in the accommodation, and then the Wernicke's has to change, okay, and this is a little bit mess if you want to compare, and also this is another problem of using the Wernicke's. So we'll never know, because there are other bases that can be used, but probably Wernicke's will be okay. There is also one thing that you have pointed out that it's very well said, that is the balancing. When you do the balancing, for instance, the spherical aberration, you say that normally it's better to be like to have unbalance. Okay, so already the Wernicke's are balanced, like the spherical aberration, but the human eye normally prefer the things unbalanced. So we prefer the shaded spherical aberration, okay, that is unbalanced. But this happened mainly because the eye has quite a lot of aberration. So normally in artificial system that has very little aberrations, the RMS from the Wernicke's are a very good value, okay? But because it will be almost the same as the Strel ratio, okay? But in the human eye, normally when you do, for instance, the refraction using just Wernicke's, okay, then they will not correspond to the subjective measurements of the refraction. It's better to have the shaded refraction, what it takes into account the unbalance, okay? So it depends, okay? Sometimes you have to do, if it's on axis, maybe using the shaded, if it's something that has astigmatism in Wernicke's. So it's good that you have done to present both of them, okay? So people know them and should have the idea what to use in each case, okay? I think that is so. Thank you very much. It was very nice. You go fast, but it was okay. But probably for people has not the mathematics background that you have, maybe it be difficult to follow. But it's really a tough thing, a difficult thing to explain that.
Yes, but I want to explain it slower. But I always go so fast.
Oh, but listen, it has been recorded, okay? So people can see it again, just put it more slowly, okay? Just speaking more slowly with a more lower speed, okay?
Okay, thank you so much, Norberto, for your talk and the explanation.
Yes, thank you.
And also, I think Matteo has a question.
Yes, thanks a lot. Thanks, Iñaki. I actually have two quite practical questions. I'm quite ignorant on this, so maybe they result naive for you guys. But one is, do you know if the pentacam. So I think the pentacam gives you an astigmatism value, or at least I have some pentacam data and they give astigmatism value. And do you think this is computed through Zernike, through Seidel, or it's something else that I have no idea what that can be? And the second question is, do you know if there are some Python libraries or something that has the Seidel wavefront already implemented and I could use or we could use for, in my case, is the anterior corneal surface, but whatever optical surface we have. Thanks.
Okay, I know that related to Cernic polynomials, there are some libraries that you can use, but related to Seidel, I haven't found anyone. I was trying to find, for example, to Python. I don't know if anyone here knows if there is, but I only have found to Cernic polynomials. And with the first question, I haven't not been working with Pentacam yet, so I don't know how is it calculating the different aberrations. But I used to see in Cernic polynomials, but I don't know. I don't know it exactly. I don't know if someone here knows how can you calculate it? How is calculated by Pentacam?
Normally, corneal topographers, what they do is they fit the elevation data. They fit the elevation data with a biconic surface or an ellipsoid. So you don't use this sort of expansions to characterize the corneal topography. You can use it then to characterize the aberrations induced by the corneal by the topography of the cornea. But to calculate, for instance, the astigmatism of a cornea, you assume that if you have a astigmatic cornea, that is like a toroid. So you fit it with an ellipsoid or a biconic surface, and you calculate it as the difference between the two principal radius of curvature. That's how the topographers work normally.
Thank you very much, Miguel.
Thanks a lot. Thanks a lot.
Yes.
Okay, thank you so much. Any question? Veronica has a question, I think. He suggests something in optic.
Okay, I will check it. Thanks. So for Zernike,
Yes.
I also have the several libraries or functions already implemented. Actually, I never heard about Seidel before today. That's why I was asking, but that's also how ignorant I was on the topic. So thanks. I will also check this.
Thank you very much, Veronica.
Okay, thank you so much, everyone. If there is not any question, we can finish this meeting. Thank you so much, Iñaki, for your perfect talk.
Thank you.
And I hope you will be successful in your project. And the next PhD talk is for Maria, I think, and it is on Wednesday, 11 a.m. that she want to talk about visual optic. We are waiting for you in that date, and thank you so much.
Thank you very much to everyone.
Thank you, Iñaki.
Thanks
Bye.
a lot.
Thank you.
Thank you.
Thank you.
Bye.
Bye.
Thank you. Bye-bye.
Bye.
Bye.